Now we can restart our top quark session, and we have the talk now by Massimiliano Grazzini, the University of Zurich, telling about top quark at the LHC and beyond. Please, Massimiliano.
Okay, so thanks a lot for the invitation. And in this talk, actually, I wanted to give an overview of top quark production at the LHC. This will be a very partial and personal overview. Actually, in the end, I realized that I won't go much beyond the LHC. Actually, so apologies for this. So this is the outline. So I will give a brief introduction, and we start talking about top quark production and decay, and I will describe our new next to linear order calculation for top production, showing some results and also its validation. And then I will say a few words about the top mass to introduce another calculation that we have completed recently, which is the extension of the NLO results in the MS bar scheme for the top mass. So I was asked to give a rather general introduction. So although with this audience, I don't know if this is really needed, but still. So it's rather clear that the top quark has a special place in the standard model. Okay, it's the heaviest elementary particle with its mass of about 173 GeV. So this means that the Yukawa coupling is of order unity, and then that the particle interacts strongly with the exboson. So also this is the top quark is the only quark which decays before hadronizing. It decays through the electroweak interaction. Particular, if you compute the lifetime, you get order 10 to the minus 25 seconds compared to the typical time scale of hadronization, which is 10 to the minus 23. And this, of course, would not be the case if you had instead a bottom quark. This is essentially due to the very high mass of this particle. So the top quark also is offer a window to new physics. Okay, it's enough to think about the fact that it drives the quadratic divergent into the X self-energy, which means that is essentially driving the naturalness problem, and as such, you need some additional contribution to cancel this quadratic divergence, for example, from new physics. At the same time, it's very standard model. It's very rooted into the standard model because the top is everywhere. Okay, it's everywhere in any analysis that you do at the experimental level. You find top quark backgrounds. Here I have just chosen a couple of examples in the case of VH, okay, VH analysis with X into BB bar, where you have this substantial TT bar background, or the classic example of WW, okay, WW, where you have IPT B-jets from the top decay, which gives an important background. So. So the main source of top events at Hadron Collider is TT bar production. So at typical instantaneous luminosities, you get about 15 TT bar events per second at the LHC, and most of these events are driven by gluon fusion, which is essentially due to the fact that the high gluon luminosity at the LHC. So these are the Born level diagram. So this is basically I mean, very roughly the process I'm going to discuss mostly in this talk. So so what is the theoretical status? Well, in one slide, the inclusive cross section is known up to 2 loop in QCD next to linear order, with the inclusion of additional resummation of threshold enhancement enhanced logarithmic contributions up to next to leading log. And this is the classic plot that you find everywhere, where you have several cross-section, inclusive cross-section measurements from starting from the Tevatron to the LAC, compared to this calculation, which was done by Chacon and collaborators already almost 10 years ago. And this, in particular, this calculation can be done for the inclusive cross-section, including this resummation at the level of differential cross-section. The calculation has been extended up to next to leading order to consider several important differential distributions. This is an example of the invariant mass of the top pair compared to the data. And to the data by D0 in this case. So, of course, the top, we said at the beginning, is it decays very, very quickly. So realistic predictions should include the top decay. So how do we do it? So we have essentially two ways. So one can use the narrow width approximation. So the narrow width approximation is based on the limit in which you take the width divided by the mass to 0, and this approximation leads to substantial simplifications because you have essentially a factorization of the production stage with the decay stage. And this approximation is also quite good because by using polarized matrix elements, you can treat spin correlations, as we will see later. On the other hand, in this approximation, you are essentially putting this top particle here on shell. So to go beyond this, to consider off-shell effects, you have to consider, for example, the complete process. So if you look at the leptonic decays, you have to consider the full signature in which you have BB bar and dilepton plus neutrino, antineutrino. And this, of course, leads to further challenges, which come from the high multiplicity phase space and interferences between production and decay. So what is the situation? There are nowadays complete next to leading order QCD and electroweak calculations for these complete final states that have been performed in the massless limit by different groups, again by the HELAC group and by Dittmeyer and collaborators already 2012. Slightly later, there was another step done by including the mass of the big quark, and essentially here completely combining in a unified framework the TT bar and the single top signature. And on the same footing, if you want, but on the electroweak side, next to linear order electroweak corrections to the full leptonic decay process have been computed by Denner and Pellen in 2016. Here you have an example of one of the diagrams in which clearly you don't have the TT bar process. Okay, you have non-resonant contributions, and you have a virtual correction which connects a virtual photon or Z boson, which connects the final state positron with the initial state quark. So, electroweak corrections, as I said, have been computed by including all these possible diagrams, and they amount, as typically it happens, to about they are large. If you look, for example, at the transverse the PTMIS distribution, they are they increase to about -15% at large PTMIS. So concerning off-shell effects, actually finite width effects of the top quark are typically small at the percent level, but they are more important than those on the W, and they can be relevant for certain distributions. In particular, if you consider the PT of the BB bar system, what Pozzorini and collaborators have shown is that if you go to high PT, you find effects which can be of the order. I mean, if you compare the exact calculation with the calculation where you include only the resonant tops, you get effects which can be of the order of 15%. So, okay, so this is basically for this brief overview. Now I would like to talk about our work that we did with my collaborators on a new next to linear order QCD calculation for stable top quarks. So the first questions you may ask after this very brief review is, well, why do you want to embark in such a new calculation? Why to do it? Well, there are several reasons. This is a very complex calculation. Actually, only one group was able to, Chacon and his friends were able to do it up to now. And actually, I have to say that the experience shows that these calculations are difficult and that an independent check is always useful. There is a long list of examples in the literature, starting from the very early pioneering work done by Van Nerven and collaborators on the Drellian, which there was a small mistake which has been corrected by Erlander and Kilgore, but even in E+E- into 3jets, there have been somehow small things that have been corrected. And even I have to say that in our group, we sort of had a problem in our diphoton calculation, which was later spotted by Ellis and friends. And more recently, even for X production in V+Jet, in vector boson fusion. So and then there is another point which, at least to my taste, is important, and Chacon and friends have never released a public program, okay, to do these calculations, which I think is useful. So so for these reasons, we have done this calculation independently. What are the ingredients? So the ingredients are 3-level amplitudes with 2 additional partons. So you can have an excellent leading order, 2 massless partons recoiling again the TT bar pair. Then you have 1 loop amplitudes with 1 additional parton. And you have, of course, 2 loop contributions, which are currently the major bottleneck. And these diagrams involve a new class of functions, and really, I mean, it's really at the limit of our knowledge nowadays. And of course, you have the 1 loop square. And then basically, if you want to have, if you want to compute fiducial cross-section and distributions, you need to have, to keep everything fully differential. And so the 3-level amplitudes and the 1 loop amplitudes with 1 additional parton are the same entering the calculation of TT bar plus jet. And nowadays they can be obtained with automatic generators, like for example, open loops and Recola. And the 1 loop square contribution is of course known, and the 2 loop amplitude is only available numerically. Fortunately, Chacon has made this work available, so there is a grid that everybody can use that provides this ingredient. And there is also work ongoing on computing this contribution analytically. But still, to my knowledge, there is nothing final about it. So all these contributions are separately divergent, and you need to use a method to cancel the singularities. So, so how do we handle infrared singularities? I don't want to enter too much into the details, but we use the QT subtraction formalism. In particular, basically, what I can say in just one slide is that the NLO QCD ingredients for the production of a colorless final state are fully sufficient to deal with initial state tradition. But once you have color in the final state, in particular in the case of a heavy quark, where here I consider a generic heavy quark that I label with capital Q, there are additional soft singularities that need to be taken into account, and these soft singularities have been, these soft contributions have been computed by Catani, Devoto, and Mazzitelli and myself, and this is the last ingredient that is needed to set up a formula, if you want, a Qt subtraction formula for this process. And the implementation is now within the matrix code. So as for other NLO calculations in matrix, all spin and color correlated 3-level and 1-loop entries are obtained with open loops. And this is really, I mean, the quality of the results that we can obtain with open loops is really remarkable. Okay, we really get an excellent numerical stability also in the infrared singular regions. The 4 Python 3-level color correlators that are needed for our formalism have been computed analytically, and we cross-check the real virtual contribution with Recola. The calculation is now fully implemented within the matrix framework, and we also have the possibility to evaluate scale uncertainties automatically. And in order to give you an idea, to give you a feeling of the time of the computing resources that one needs to do this calculation, to get per mille accuracy for fiducial cross sections, we need order 1,000 CPU days, which means that if you have a cluster with 1,000 cores, which nowadays is not sort of impossible, you get your simulation within 1 day. So let me show a very quick comparison between our results and Top++. Of course, once you do such a calculation, you want first to validate it, to make sure that everything is fine. And indeed, we have a very nice agreement with Top++. And I should say that the only ingredient that we take from the literature, that is the 2-loop amplitude, gives a very, actually by chance maybe, but it gives a very small contribution to the cross section. So it's really at the per mille level. So we can really claim an almost completely independent result with respect to Chacon and collaborators. So we also have validated our results at the fully differential level. So this is an example of the comparison between matrix and the calculation by Chacon and Mitov. And you see that even at the level of distributions, we get agreement which is better than 1%, even in extreme kinematical regions. And here also for the rapidity distributions. So now I'm going to flash some results. So we use for these the results I'm going to present, we use an PDF 3.1 and we compare with CMS data in the lepton plus jet channels, which are extrapolated at to Python level in the inclusive phase space. So in order to match what CMS does, we have to extrapolate, we have to use ourselves fully inclusive to the calculation without cuts. And of course, we have also to adjust for the branching ratio. And so one comment about scales. So of course, perturbative results depend on the choice of renormalization and factorization scales. And these scales have to be chosen of the order of the characteristic hard scale of the process. So if you have an inclusive cross-section, the hard scale is of course of the order of the top mass. And the same can be said if you look at the rapidity distribution. If you look at the invariant mass distribution, of course, you have another scale, which is the invariant mass itself. While if you look to transverse momentum distributions, you have essentially the transverse mass, if you want. So what we find is that a dynamical scale like HT/2, which is the average of the transverse masses of the top and the anti-top, turns out to be a good approximation of all these characteristic scales. So this is our recommendation for the scale choice. And of course, scale uncertainties are studied in the standard way by considering independent variations of μF and μR. So I just flash a few results. So a classic result is the PT distribution on the top that is found, as it was already known, to be, I mean, the measured PT distribution is slightly softer than the next to linear order prediction. And so what we see is that the perturbative prediction is relatively stable when going from next to linear order to next to linear order. And we, nevertheless, despite this small tension, data and theory are consistent within uncertainties. And we have also compared to the results for the invariant mass distribution. So here we have a very nice description, except the first bin, okay? So here I have to say that here there are several issues that can come into play. Of course, there is the extrapolation. So to extrapolate at the parton level for on-shell tops, you have to do some cooking, okay, with Monte Carlo. So I mean, it's not, I think it's not unreasonable that there can be some issue close to the threshold, which is exactly the most delicate region where this extrapolation may fail. And also one should, it's a very trivial observation, one should remember that this of course depends on the top mass. So if you take a smaller top mass, you open up the phase space in this region here, and you get a higher cross-section. Indeed, I mean, a smaller MT, just by about 2 GeV, leads to a higher theoretical prediction and a better agreement with the data. Of course, there is also there are also theory works which try to explain this discrepancy by I mean, with a further perturbative corrections or non-relativistic corrections. But I mean, I don't enter into this. I also I observe that the analysis by CMS in the tonic channel leads indeed to a fit of MT order 171 GeV. So with our code, we can also compute the double differential distribution. So this is an example. So it's a rapidity distribution in 4 bins of invariant masses. And again, here in the first invariant mass bin, you see essentially the same effect, which is however diluted due to the very large bin sizes. Here I'm integrating between 300 and 450 GeV. So you see that there is still some tension, but it's much more reduced, and there is a better agreement with the data. And for the other bins, we have a relatively good agreement with the data. And it's nice to see that now, I mean, the experiments are using the code. Actually, unfortunately, we still don't have the calculation implemented in the public version, but we have a private version that we have provided already more than a year ago to Atlas and CMS. And here, this is an example of a study done by CMS where they really use the code themselves, which is very nice. And here you see the same issue that I have discussed before in the PT distribution of the top. Okay, here there is theory over data, so the sort of the tension, I mean, the slope is opposite, but it's exactly the same issue. So, of course, while we were working on this, our competitors are very strong, and they went on. Okay, so they have done this really impressive piece of work, which is the inclusion of the top decays within the narrow width approximation. This is really a beautiful work where basically they have included consistently QCD corrections up to next to linear order to production and decay for the first time. And this work raised quite an amount of questions. Okay, in particular, they have shown that if you compare, for example, here I don't have the time to enter into all the details, so I've just taken the distribution delta phi, which is the azimuthal separation of the leptons in the transverse plane. And so this distribution, if you do the comparison with the data in the fiducial region, you, both for Atlas and for CMS, you observe a very good agreement between the next to linear order result and the data. If you do the comparison at the inclusive level, that is after the extrapolation is done, the same data, okay, there is a small tension, which probably tell us that there is still something we have to understand in the extrapolation, okay, and at least to my understanding, this suggests that this comparison should be done at the fiducial level, which is really the reason also why we theorists make big efforts to do these very complicated, fully differential calculations. Okay, so this is this is basically, if you want, the status, okay, at the moment, the best that you have at the level of QCD radiative corrections. So, of course, these are still calculations at the parton level. Okay, so then the question that you may ask is, okay, but how can we sort of use this within analysis? And of course, this you cannot do it directly unless someone makes the effort to find a way to implement it into a parton shower. Okay, and this is what these people here, Mazzitelli and collaborators, have done recently by doing the first NLOPS calculation for this process. Basically, now the next linear calculation for stable top quarks has been deployed into the first calculation matched to the parton shower. And here, basically, the all-order radiative contributions are implemented through the shower using the so-called mean LFC method. Here, I don't enter into the details, just what I want to stress is that you have a calculation which has formal next to linear order accuracy. Actually, they also have higher order stairs, which are sort of spurious, which are in their method, but they control exactly all the next to linear order terms, essentially using, if you want, what we did at the parton level. And but however, they have it they also have the effect of the shower, so they have really a generator for this. And this is an example of some results. So you have the PT on the top, and here, if you remember the previous plots, what you see is that, of course, this one cannot expect that the shower improves the agreement with the data for this observable. I think indeed, basically the theoretical prediction for from the mean law PS is essentially perfectly consistent with the next to linear order results. So there is no improvement in the description of the data. Here in the PT of the top pair, there is some slight improvement in this region. However, honestly, I'm not sure whether this could be considered genuine, okay, because in this region of PT of order 200 GeV, I suspect that this could be due to sort of the method itself, not really, because the shower somehow in this distribution must give the crucial effects in the only in the small PT region, I would guess. In any case, the two predictions are perfectly consistent within the uncertainties. Okay, so now top mass. So of course, the top mass is a fundamental parameter in the standard model. We know that with the current values of the top NX masses, the vacuum is metastable. Okay, so this is clearly an important parameter. And so direct measurements of the top mass are those in which the top quark is observed through its decay products. However, if we remember, the top quark is so heavy that it decays before hadronizing. So essentially, we can view the top quark as a physical, though unstable particle. And in this sense, the pole mass is the natural definition. Okay. However, we know that the quark mass is also given by the accompanying gluon field that you have. Okay, so if you integrate completely over these gluon modes, the pole mass definition includes the surrounding gluon radiation up to infinite distances. So in a sense, it's really sensitive if you want also to large scale effects. Alternative, one can keep just the contribution at short distances, the contributions below 1 over mu, or if you want at energy larger than this scale mu. This is what you do when you define sort of a short distance mass. So this is a compilation, a recent compilation of measurements of the top mass. So as I said, direct measurements can be considered as measurements of the pole mass. And the question arises when the precision, which is currently at a level of better than 1 GeV, will improve. Okay, this is, for example, a projection from CMS, which shows that one can expect an uncertainty, the uncertainty going down to less than half GeV. So, but let's be a little bit more precise. Okay, so if you want, the first comments I made were rather rough. So I'm a theorist. Okay, so I know that the top mass must be properly defined by renormalization of the related ultraviolet divergences. And in the pole scheme, what is the pole scheme? The pole scheme is the scheme in which basically you fix the pole of the quark propagator at any order in perturbation theory to the same variable that we call capital MT. So, on the contrary, in the MS bar scheme, the renormalized mass is defined by subtracting ultraviolet divergences in dimensional regularization, and therefore the pole of the quark propagator receives corrections at any order in perturbation theory. So these two prescriptions are related, of course, and the relation is known, actually is known up to 4 loops. So you can express the pole mass in terms of the MS bar mass perturbatively. At the lowest order in alpha S, they coincide. Once you include corrections of order alpha S, they are different. So, however, as we have seen before, the pole mass is sensitive also to long distance effects. So, and in particular, this, if one looks more closely, it means that it is affected by the so-called renormal ambiguity. So to make a very difficult problem very simple, essentially what happens is that if you compute these diagrams here, the corrections to the top self-energy, what you find is that the coefficients of the perturbative series are factorially divergent, and the series is not Borel summable. This leads to an ambiguity on the top mass, which is of the order of lambda QCD, which is roughly 200 MeV. Actually, one can make, of course, these statements more precise, and there have been recent works that have tried to make to quantify better this ambiguity. However, these works do not, I mean, the results do not precisely agree, and they find that this ambiguity ranges between 110 and 250 MeV. So this is the order of the order or better than the accuracy that can be reasonably achieved in top mass measurements at the LSE. Okay. So, however, let's go back to the MS bar mass. So, as I said, okay, it can be interesting to compute predictions which, instead of using the pole mass, use the MS bar mass. So let's add a few more comments about it. So the MS bar mass depends on another scale, which is a renormalization scale, which is similar to this QCD, the scale of the QCD coupling, which we typically call mu r. Okay, so if I want to use the MS bar mass, I have to introduce another scale. And the dependence on this scale is controlled by a well-known renormalization group equation. whose coefficients are known up to quite a high order. So if you look at what happens at the lowest order, and you compare, for example, the running of the top mass with the running of alpha s, what you see is that the speed of running is lower for the mass. So the scale dependence of ms bar mass is lower than the one of alpha s. This is one comment that sort of will also enter in the later discussion. So of course, the ms bar mass can be specified by fixing a reference scale plus using a renormalization group evolution. Typically, what people do use a definition which they use this m bar definition, which is essentially the scale up to which mt of m bar is equal to itself. So the typical values, so for the pole mass, we said it already, it's under 73 GeV. For the ms bar mass, it's lower, it's about 10 GeV of difference, okay? And this difference is much larger also than if you want the normal ambiguity, okay? Note that this is scale dependent, so if you choose a renormalization scale which is modeled, for example, is m bar over 2, what you have is that you get an ms bar mass which is of the order of the pole mass, okay, simply because the first coefficient of the renormalization group equation, or actually of the conversion between ms bar and pole, is vanishing for this scale. So, so one can already draw two consequences. So the perturbative QCD predictions that if you use the ms bar mass, unavoidably depend on a third scale, which, if you want, you can identify with the renormalization scale, but in principle is different, and on the standard mu r and mu f. And one can set this scale to a scale which is different from NT, somehow to embody possible higher order effects. And this is what we call running mass effects. So, so now, having said that, what we can do, we can try to convert our predictions from the pole to the ms bar scheme. So one can start from the on-shell cross-section, which depends total or differential, which depends on the pole mass, and simply replace the pole mass with the ms bar mass. Of course, formally, you can, if you do an all-order replacement MT into the ms bar mass, you have an all-order equality, okay? You have the cross-section in the ms bar scheme will be equal to the cross-section in the pole scheme. But if you truncate this expansion, you will get quantitative differences. So what one can do, one can define, one can expand in alpha s up to next to leading order and define our next to leading order ms bar cross section in this way. And if you play this game, what do you find? You find that, of course, at the lowest order, the results are identical. You just replace the pole mass with the ms bar mass. Once you go to next to leading order, there will be, in the next to leading order cross-section in the ms bar scheme, there will be a term which is obtained by simply replacing the pole with the ms bar mass, but then there will be a term which depends on the derivative of the leading order cross-section with respect to the mass. And the equation that you get is slightly more complicated once you go to next to leading order. However, all this is trivial if you want. It's just enough to sit down and obtain these coefficients. So, however, these mass derivatives that I have in these expressions can be very sizable and spoil the perturbative convergence of the ms bar cross-section, in particular in the threshold region. So what do we expect? We expect that at low orders, the two cross-sections can give consistent results within uncertainties, and at higher orders, we expect that the results should be quite similar. Okay, So we present results. I will present results which depend on these three different scales, which can be varied independently by a factor of 2. And instead of the classical 7-point scale variation, we get a 15-point scale variation. And we compare pole and MS bar results by using this setting. So this is the pole mass scheme we use as 173.3 and 163.7 for the MS bar mass. So for the total cross-section, if you compare pole and MS bar results, you see that there is consistency, but you observe immediately a typical feature of the MS bar results, that they show a faster apparent convergence, which has also been sort of advocated as a motivation to use the MS bar mass instead of the pole mass. For example, if you compare the next to linear order K factor with the pole mass, you get 1.5, while you get 1.3 for the MS bar, and the corrections are almost negligible in the next to linear order in the MS bar scheme. So there is a technical explanation for this. Okay, the explanation is that at linear order, the MS bar cross section is obtained by evaluating the pole cross section with MT equal to 163 GeV. So the mass is lower and the cross section is higher. So already at linear order, you have a higher cross section simply due to this kinematical effect, if you want. And also the other comment I want to make is that this result is strongly dependent on the choice of the central scale. For example, if instead of using M bar, you use M bar over 2, the convergence of the MS bar expansion is slower with respect to the pole scheme. And on the other hand, we know already from the studies by Chacon and the collaborators that if you take MT over 2, you get an apparently faster convergence of the series in the pole scheme. So actually, this is also, I mean, something I think important to remember. So having said that, we can go to the differential results. So I don't know how much time I have. Still, I hope I can.
Yes, sure.
Yes, so I went slower than I expected, but still. Okay, so I'm almost done. So these are results for the, basically, here I'm comparing results for the PT distribution on the top, for the average PT, in the pole and in the MS bar scheme, and then I'm taking the ratio. And the comparison shows that the overall features are very similar, okay, in the MS bar scheme, and the two, in particular, when you go to higher order, up to next to linear order, you see that there is perfect consistency between the two in this ratio. And now I come to the point of the invariant mass distribution. So CMS has measured the invariant mass distribution and compared their data with an extra linear order calculation with a fixed MS bar mass, and they have fit the value of M bar to the data in each bin by using this fixed scale. So so we have criticized this measurement. Okay, they have claimed that they observe running mass effects, but in our opinion, such a study has to be done by using a running bin-dependent value of the renormalization scale for the top mass. And one has two options. Either you can either use a completely fixed scale, and then you would get an extension to next to linear order, what CMS did, or you can use a dynamic scale. So we have investigated ourselves this issue by trying to see whether we could see effects of the running. And we have done this by, so first we do, in this plot, we do a calculation exactly as with the same setting, the same beans that CMS has used, but using here a fixed scale, and here using a running scale, where the central scale is set, if you want, to the average of the bin, invariant mass bin, that was used also by CMS. And basically, of course, at low invariant masses, you don't expect to see differences. The differences at high invariant masses are small and are mainly driven by the running of alpha S and the PDFs. So basically, what we observe is that the effect of the running of the mass is really very small. This can be seen by looking at this dashed line here, because this dashed line shows results that are obtained with the dynamical scale, but fixing the scale of the top mass. Okay, and if you compare the two results here, dashed with solid, what you see is that the dashed line is completely within the scale uncertainties of the prediction. So our conclusion is that, okay, next to linear corrections lead to a reduced theoretical uncertainty and to an improved agreement with the data, but we don't see sensitivity to running mass effects. Of course, one should also say that when you go to high masses here, I mean, in principle, asymptotically, you go into a regime in which resummation would be needed, and this of course has already been addressed in part in the literature. So so I can now conclude. So I have given a very brief review of the status of theoretical predictions for top quark production at hadron colliders. And I have presented a new calculation of heavy quarks at the next order in QCD. I've shown that our results are in perfect agreement with the results obtained by Chacon and collaborators. And I stress that this is really a non-trivial check, because the two computations are carried out with completely independent methods. The program is available now since quite some time to Atlas and CMS, and we hope very soon to be able to release a version of the public version of Matrix where the calculation is implemented. At present, it is just, if you want, a dedicated version which is only for this process. And in general, I can say that there is an effort in the theory community to improve the tools, to improve the calculations to match the precision that can be expected, in particular in the high Lumi LAC. And in the second part of the talk, I have discussed very briefly the issue of the top mass, and I think one can say that when precision of the measurements will approach the scale of lambda QCD, top mass measures at hadron colliders will pose really deep theoretical questions and also challenge our understanding of the QCD in the non-perturbative regime. So we have extended our next linear calculation to the MS bar scheme for the top mass. This is, if you want, it's a formal reorganization of the perturbative expansion. And now with this change of scheme, if you want, you get a calculation which depends on 3 scales. So you have to study 15-point scale variations. The MS bar results show an apparent faster convergence with respect to the results in the post scheme, but this depends on, as I've shown, on the central scale choice. And then basically the shape difference that we observe are reduced by including higher order corrections. And we have also shown a first study of running mass effects. And basically we don't see significant sensitivity to running mass effects. Thank you very much for your attention.
Thanks a lot, Massimiliano, for the basically nice explanation of all your efforts, recent efforts in this challenge. Questions or comments? Yes, Pierre. No, sorry. Roberto.
Yes, it's very nice. If I understand correctly, I mean, we are close to have the possibility to use the NNLO calculation interfaced with Parton shower. So, I mean, essentially in Monte Carlo, in order to be able to do the analysis.
Yes, yes.
The values.
Yeah, this is, of course, I mean, one can argue whether what is done with this method is the best that you can do, okay? Because basically, I mean, they are essentially what they do. They have a leading log shower, okay? They completely give up, if you want, with the shower. The shower is the same that is used everywhere, okay? So if you do an extra linear recalculation, you would like also to have a better shower. But I have to say that this method is extremely, I mean, what they do is extremely convincing, okay, to me, because, for example, I mean, if you compare other calculations which have been done, which are similar, okay, for color singlet, that is, for example, for X production, they agree for the PT distribution, which is, if you want, the most important, I mean, the observable, which is sensitive to really to initial state radiation. Their implementation works even better than I would have expected, I have to say. So they agree with the resummed calculation, which have much higher accuracy, very nicely. So I think this is really the effect of the fact that they have exact NLO corrections implemented. And yes, so this, I think it's a first step in this direction, but it's a very nice achievement.
Would you agree that these close completely at this point all these discussion concerning we do not know what it is the Monte Carlo, this is the Monte Carlo mass, and whatever? I mean, all the ambiguities related to the top mass that you have discussed, they are there because these are theoretical ambiguity. But if you use an NLO calculation with the appropriate Parton shower description, at that point we know what it is then the Monte Carlo. It is the pole mass at that.
Yeah, I mean, actually, I'm always, I have to say that I mean, I'm always confused when I hear about the Monte Carlo mass.
Me too, I have to say.
I mean, the Monte Carlo mass, what is, I mean, it's so the parameter that they have that you have in your simulation tool, to me, is the pole mass, because, I mean, as I said, I mean, the top, the case before hadronite, so you can basically treat the top as a physical object, and then the pole mass is the mass that, in my opinion, that is measured the LAC with this direct measurement. So I think, I mean, in a sense, yes, I think I agree with you. Definitely, it will be an issue when you will do better and better in your analysis, and you will get sensitive to your precision will improve to the level that we don't know anymore if what we are measuring. But at this stage, still, I think there is still some time. So maybe the theorists in the meanwhile can do some additional work.
Okay, thanks.
I was distracted. I don't know who is the first, but I would say Marco, please, and then.
Yeah. Thanks. Yeah, I was the first.
Okay, thank you. Sorry.
Thanks, Massimiliano, for nice talk. I wanted to ask related to the pole mass. First of all, when you choose the value of the MS per mass, what do? You do the conversion from the pole mass, or do you take the value of the MS per mass from some other?
No, I think that there, what we do, so we use, I think we use 3-loop conversion. I don't remember, but I mean, that value is what corresponds to our pole mass doing the conversion. Okay, we use this code, which is crank deck, to do the conversion, but it's basically not independent in a sense.
Okay,
So
it's
we start from 173.3 which is the pole mass. This is the reference value, and then we convert to MS bar, and we get this 160. I don't remember anymore what is the value, but I mean, it's a fixed 163.7.
Okay. Now, the other question is related to the conversion. I mean, if the mass is the mass that appears in the diagrams in the propagators, then it's fine. But if you have the mass in the phase space, in the kinematics, theta functions and delta functions, that is, I mean, for instance, close to threshold. The threshold is given by the mass, and that mass should be, I guess, the pole mass, no? So when you do the conversion, do you convert that value as well at a given order, or do you keep?
No, I mean, the conversion is done consistently, both in the matrix element and in the phase space.
So if you have a distribution that starts at a given value of invariant mass, this threshold moves when you do the
yes. So you get, of course, I mean, so this should be said. So it's definitely not, I mean, this calculation is not something that you would use close to threshold, okay? Because close to threshold, you are sensitive to the physical mass, which is the top mass, which is the pole. Okay, so however, there is no way. I mean, there was also, I think, I mean, I don't want to make very definite statements, but I mean, I think it was Michelangelo Mangano who made the comment in one of the presentations that were given on this work, that yeah, it would be nicer to have to make this replacement only at the matrix element level and keeping in the phase space the pole mass failure. But I mean, we thought about that, but I really don't see how this is possible, because I mean, then you have to tell me how you deal with the LSZ reduction and with the basic of quantum field theory, essentially. So, I mean, what we do is really, I mean, you take the increased cross section. It's a function of MT. You simply replace order by order the expression of the pole mass in terms of the MS bar mass. So if you could do this at all orders, you would get exactly the same result. Of course, you cannot do it at all orders, and so you get differences, which, okay, as I've shown, are reduced when you go to higher orders.
Sure. Thanks.
Okay, Stefano, please.
Ciao Massimiliano, grazie per la bellissima
risposta.
Ciao, ho una domanda sui risultati differenziali per la sezione d'urto in relazione alle correzioni elettrodeboli.
So maybe you should speak English because...
sorry, yeah. So I have a couple of questions about the differential cross-section results for the TT bar cross-section in relation to possible electroweak effects. I don't know whether you covered them. I missed the first 15 minutes of your talk, apologies. But you show, for example, the high PT distribution of the top, and there the theory was overshooting the data by some 5–6%. I think you also had results for the eta distribution and large invariant mass, where you had a similar discrepancy in the same direction. So when we did the calculation with Doug Ross 15 years ago of the one loop electroweak correction to TT bar, so these are of order alpha A square, alpha W, we saw precisely, no, it's another plot actually where it's most evident. We did see that in those kinematic regions, you had negative effects coming from the Sudakov leading loss.
Yes. But yeah, sure.
And also the TT bar threshold at 350, there were fun effects coming from the interference between the QCD bit and the triangle diagram with the Higgs boson, and also with the lambda and Egan suppressed Z propagation. Has anybody been looking at putting this correction into Monte Carlo and throw them against the data alongside the N analog QCD effect?
So, there has been so an explaining order electroweak effects, as you said, they are known, but I mean, at present, I think the only study that I know is the one that was done by Chacon and again and collaborators, where they have shown some distributions combining together with simply by using additive and the multiplicative combination, electroweak and analog QCD. So I'm not aware of detailed studies, because actually, again, I mean, if you want to do it, you can do it in explaining order. You take probably you take math graph and then you can do it. But I'm not aware of studies. I mean, it would be certainly interesting. This is something we also have in our agenda in trying to put together also electroweak corrections and to make them available, because again, once you have a code that computes everything, then you can also make more detailed analysis and comparison with the data.
Yeah, I think it's slides 24 is a nice illustration of what I meant.
Here?
Yeah, I think there you are kind of undershooting data. So theory is overshooting data, I think. So you would need.
You mean in the high invariant mass bin? Okay, yes.
Yeah, and also I think you had some distribution in PT. So I don't think you can do it with MATGraph, because it's actually mixed one loop process.
Okay, I see. Okay.
So you get it by
okay.
So you really need to turn some dedicated calculation into proper Monte Carlo. I mean, we didn't, but I think Ben Reuter did, and also Hans Kuhn did. So it would be interesting to throw those corrections against these data, because you would explain many of these anomalies that you seem to be finding in the high mass region, or the IPT region, or the central region in ETA for high invariant.
I wouldn't call them anomalies, because, I mean,
yeah.
All in all, I mean, I see a relatively good agreement. Okay, I mean, okay, there is one point which is off with respect to the next leading order, but all in all, and I mean, the most I would say the most evident effect, which is however very well known by now, is in the PT of the top, and this I don't think that you can have you can improve on that, but maybe it's possible. I don't know. One should think about it.
And you should also check the threshold region 350, because there you have these fun interferences between the glue to TT bar and the triangle diagram with the Higgs, as well as the triangle diagram with the Z, which is suppressed by Landau-Ian. But if you propagate the Goldstone component, that is just as big, which is allowed by the Landau-Ian theorem. That's just as big as the Higgs mediation. So I think you should throw those, because you would see some effects, not inclusively for sure, but differentially in certain regions.
Okay.
Marcel?
Yeah, this was initially a reaction to the discussion between Roberto and Massimiliano. I'm going to try and propose a view on this issue with the Monte Carlo mass, and then you can tell me if I get it wrong or not. So, a priori, the matrix element that's in the Monte Carlo is next leading order. It's done in the pole mass scheme, so it's clear that, right, at least initially, the pole mass should be close to the Monte Carlo mass. Now, then we add on the Parton shower, hadronization, underlying events, all these additional steps. And the observables we use to do these direct mass measurements are quite sensitive. Right? The top mass peak will shift by a couple of GeV when you switch on some of the soft physics effects. Now, if the part and shower randomization were exactly correct, that would still not be a problem. But of course, we know these models have limitations. So we have to somehow understand how the top mass peak shifts by anything beyond the matrix element, and then assign uncertainties to that. Now we have a procedure to do that. We compare Powig Pythia with Powig Herwig. We vary different models, and we define an uncertainty as the variation. Now you could have a long discussion whether that variation covers the uncertainty. There are theory studies that show that by the part and shower cutoff subtly changes the mass definition by order 500 MeV, and you could be worried that that might not be fully covered. I'll leave that for the theorists, but generally, I think we continuously discover features of the Monte Carlo. Color reconnection is an example, but we're also studying off-shell and interference effects with WT, and these can shift the top mass that you would extract from a measurement by 300, 400, 500 MeV. In Atlas, we're now looking at the recoil of the second gluon in the top decay. Again, you can get very sizable shifts in the top mass, and it becomes very difficult to define exactly which variations you should include as your modeling uncertainties. And I think that's the key issue here. So it is the pole mass to a good precision, probably 500 MeV or so, but it's very hard to get that uncertainty exactly right. We always have these ad hoc 2-point variations. Yeah, sorry.
Just for clarity, when you say you do all these variations, you are assuming that you do them while describing all the data at the same time. Is that correct?
Right. That is part of the difficulty. So you should
your microphone is
variations, and we
excuse me, Marcel, we cannot hear you now.
Yeah, you're right.
Okay.
That is an important point. So you shouldn't just blindly toggle switches in Pythia. That is dangerous. So we should retune. We don't have retuned Monte Carlo setups for all these variations. So some of these ad hoc variations are overestimates. I will grant that. But still, the key difficulty, I think, if we want to go to a 200 MeV top mass measurement with this method, is to identify a sufficiently solid set of variations that really covers everything that could possibly go wrong in the part and shower, in the hadronization model. And we're making progress where the prescriptions are already quite a bit more refined than just comparing Pythia and Herwig. But yeah, whether we can be confident that we can play this game and reach that 200 MeV precision in the next 10 years or so, the jury is not out. I think we'll see how far we get.
Okay, Roberto, do you have an answer to this, or?
Yeah, I have a comment. I mean, Marcel described it very nicely, or the series of operations that one does in this case to understand what are the systematic uncertainties. However, this sort of complicated study are not different from any other study of observables that are done even in the electroweak widths. I'm thinking about the asymmetry, for instance, and interpretation from related to sin square theta. And if you look to the number of corrections that are done for this G-2, you have corrected, there is no QCD, well, there is QCD in a way, but in a different way. They are there as well. I mean, we live in a world of pseudo-observables. The reason I don't like all this calling it Monte Carlo mass is because it drives away, I mean, it obscures the real problem, the real issue. Now, it gives the impression to the community that we don't know what we have done with the Monte Carlo. We know what we have done with the Monte Carlo. We have to compute correctly the uncertainties. And still, what is peculiar of the top mass is that the fact that we have this issue of the color flow from top to the B, with these effects of connection or reconnection that are very difficult to pin down. And these, I mean, we should understand what are the real studies to be done in order to understand well that effect. But this has not to do to knowing what it is in the Monte Carlo. So this is the reason I'm constantly fighting about this, this idea of focusing on the issue of the Monte Carlo mass. And I hope that we go more and more into the direction of understanding better and better the real issue. So it's no more than that, but I mean, I totally agree. I mean, it's very difficult to make consistent measurements. It's very important to understand what are the different systematics in different techniques. So I mean, the list of issues that Marcel, that you have described, these are real issues. I mean, of course, we have to understand them. This is the general. In my opinion. I had another question, but on a different topic.
But just to
Massimiliano,
to say something on this, we grow up with the notion that quarks cannot be seen, but then we meet the top quark.
Exactly. So this is the problem.
So we have to resolve 10 years of background where we are taught that top single quarks cannot be observed.
Still, I mean, we should acknowledge that we have done enormous progress since, I mean, the first time I heard this discussion about the issues related to the top mass was at top 2008, it is 13 years ago. We have to acknowledge that we have done enormous progress in 13 years. I mean, at the time, I remember in a conference room, we were discussing whether we at LFC we were finding effects of the order of 10 GeV. I remember exactly 10 GeV were quoted by simply studying the PT dependence of the top mass or similar kind of effects. Now we have a list of measurements, including measurement with single top, which have a very different color structure, and the endpoint measurement and whatever. And it happens that, I mean, we don't see large effects. I mean, we are bound to the effects that we are these effects that Massimiliano was talking about, order of lambda QCD and whatever, but still, we have all the list of issues that Marcel described that are there. We cannot deny that they are there. So I mean, we are in a more normal. I mean, the progress was really significant, and I think that this fact that now we have this NNLO calculation interface with the part shower is another step forward to understand better and better this issue.
Agreed.
Yeah, but although I don't know if Massimiliano, you have, for spin correlation. This matching with the Barton shower, take this into account. You know if this is
I don't. I think that it is. But
because if the original NNLO computation didn't provide the LCT configurations.
I think no, for sure. I mean, the virtual and everything is done with a stable top quartz without the spin polarization. In principle, it could be done, okay, because the virtual is available. I mean, the virtual is available with.
And your method is certainly spin independent.
No, but I think so. This is the very first, as you know. I mean, it's something that appeared just a few months ago, and I don't know if it's already public. Probably it's already published and available. I don't know.
Okay.
But it will come, I guess. I mean, I'm not involved in this work, but I guess it will come.
Good. So, Stefano, do you have some more questions?
Yeah, it's a new question. I don't think you only covered cross-section observables. You didn't cover asymmetry observables. So following on what Francesco said, one of the added bonus coming with the top being a free object is also the fact that it decays into object for which you can measure the direction and the charge of the B jet and the lepton. So you can define what are called charge asymmetries, like the forward-backward symmetries, or spin asymmetries, which in jargon you call AL, ALL, where you essentially capture different combination of the spins, the polarization of the tops at production level. Of course, you don't have a polarimeter in the detector, so you look at triple product correlation between lepton and B quarks and B jets. Now, those are certainly interesting from a BSM perspective, because what may not appear in the cross-section may appear in the differential distribution of the symmetry. But they're also interesting because they can reveal fun effects which are exclusively of standard model origin. I think all of us, we remember the anomaly seen by Tevatron around twice the top mass, which people thought it could have been an evidence of new physics, but it was at the end of the day just an effect coming from the one loop QED correction, a Coulomb effect, some absorptive part in the one loop amplitude. So what's the program at the LHC in terms of looking at these asymmetries alongside the cross-section at the best level that you can, so including the NNLO QCD correction, the NLO electroweak. And the question is also technical, because sometime in doing this calculation, you're not fully exclusive. So you're not actually able to define the forward-backward symmetries. What's the status there?
So, I mean, I think, if you ask what the status of the measurements, maybe Roberto is better.
No, I was asking from the theory point of view, whether you can define this asymmetry at the same level of accuracy as you can.
So if there is, with our calculation, we could compute easily, with our program, we could easily compute the charge asymmetry. However, these are results that have already been obtained in the literature, again by Chacon and the collaborators, also including electroweak corrections. And I think that, if I remember correctly, the effect is very small. Okay, I mean, it's not somehow we have not put it at the top of our priorities. If there is something particular, also when the case will be included, that it would be worth to study, definitely. I mean, I'm interested, but this is not at the moment. I cannot really answer because we didn't really look at it in detail. Okay, Roberto, your hand is raised.
Yes, it is the other. I wanted to understand what was, let's call it, the mistake or the difference done by CMS in this running of the top mass. Is that the running of alpha S and the PDF were overlooked because you redid it, and that was the cause of the difference, or it is the treatment? You mentioned that, but I wanted to understand it a little bit better.
Okay, so you are still recording. So okay, so then I have to be careful what I say.
Yeah, but these are informal discussion.
This is a very delicate point. Okay, so let's put it like this. So in the first paper, what they did was they did the following. So they do a measurement. Okay, so the measurement, of course, it's a measurement, and I mean, it's a precision measurement of the invariant mass distribution. This is, I mean, it's fine. Then what they did was to compare this measurement with an extra linear order calculation by using the MS bar mass. Okay. So what they did was the following. So they didn't do the measurement into 1, 2, 3, 4 MS invariant mass beams, and they use a fixed scale. So the mass in the MS bar scheme is M bar, that is M bar M over M.
Yes.
And they fit, so they take this next linear calculation, they use M bar as a free parameter, and they fit the value of M bar that they obtain in each pin. Then they use the renormalization group to evolve from M bar to the central value of each pin. And their conclusion is that they observe that, of course, if you use the renormalization group, then you see the running, okay? But I mean, our point is that you are injecting the running, you see the running. So, I mean, you cannot. They obtain essentially compatible with this fit. They obtain essentially compatible values of M bar. And by using the renormalization group, then they observe that the values of the runned values of the mass bar mass are consistent with the renormalization group, which, I mean, is not, in my opinion, is not, it doesn't mean, actually it means that there is no effect of the running. It's the opposite, okay? So it's really, so in a sense, our problem with this work is really I mean, what do you define? What do you mean when you say we have observed the running? I mean, in my opinion, I observe the running if I compare the data with the theoretical prediction, which doesn't include the running. For example, here, okay, in this plot here, I compare a theoretical prediction obtained with a dynamical scale, but with a fixed mass, okay, with which is the dashed line, with the theoretical prediction where the mass is running. So there is a difference, but the difference is much smaller than the theoretical uncertainty. Mm-hmm. So my interpretation of this result is that there is no, I mean, there is no sensitivity.
There is no sensitivity.
To the running. Okay. Okay. So my understanding. So then they have a sort of. I mean, they have considered our criticism, and they have redone their analysis now by putting by using the dynamical scale also for the mass, by using also a running mass. And they claim, and honestly, this I didn't understand how they can, but they claim that they get the same result. I mean, one problem of this second, so this was presented at top 2020. So one weakness that I see in what they did in this second step is that, okay, now they used the running mass, but they didn't, I mean, they didn't study at all scale uncertainties. So scale uncertainties, as you can see, are very large, even in next to the order. Mm-hmm. So again, it depends what you mean by sensitivity. If of course, if you set the errors to 0, then I mean, then it's okay. Different. So I mean, it's really so for us. I mean, so for me, let's put it like this: it's very difficult. So we basically think that it will be hard to see anything.
Okay,
it is observable.
By the way. Marcel, just if possible, I want to continue a little bit on this with a small question. I see your hand raised, but just I want to ask you to pass in for a second, because well, in your computation, we see something relatively new in a certain sense, in which we vary 3 scales. No, in general, we work with the 2 scales, and we vary the 2 scales. And there is a meaning in varying them above and below. Okay, but I'm asking if also to myself, is not that, I don't know if you have a clear idea on this. Well, as for the strong coupling, we understand that the scale we use there has to represent the typical scale of the process. In some sense, in this way, you hope to resum, I don't know, to take into account extra effects. Okay, But for the scale of the quark that is produced, okay, I wonder if it is not a bit of an overshoot to vary and take also for that parameter, I don't know, a wide range or something that is.
Well, I mean, I don't see the difference. Okay, in a sense, you have a running mass, and you choose this renormalization scale as the typical scale of what you are doing, like for alpha S. So, I mean, if you are looking at an invariant mass distribution at 1 TeV, I mean, 1 TeV is much larger than 170 GeV. So then, in that case, I think the natural scale is 1 TeV, or maybe half of it, but something of that order. I mean, so, I mean, if you want, you can also. I mean, it's a different topic.
No,
but
let me complete. Sorry, excuse me. I would have thought, okay, I produce this quark with I produce a pair of them with very high invariant mass. Okay, the vertex I'm probing at this very large scale. But the running of the mass, probably wrong, but I more see related to, let's say, the propagation of this particle. Okay, once it is produced, I am not really probing a vertex. So
I mean, it's a different. So this your question sort of reminds me what happened with the MS bar mass, the scale of the MS bar mass in double X production and in the XPT distribution. So it's a different thing. Okay, here we are producing the top quarks. In that case, the tops are virtual. But for example, I was ready to bet a couple of years ago that somehow this was the scale should have been taken of the order of the mass itself, that one should not really look at the dynamical scale. But there is this work done by Spira and collaborators, which I think has shown that even there, even when the top is virtual, you have to choose the right scale. So if you choose the wrong scale, you don't get the correct behavior. So this work is quite nice. I mean, Michael Spira have I mean, I think they have sort of understood how to choose the scale. I mean, because it makes a huge difference. I mean, for example, in double X production, there is, or even in the PT spectrum is even more complicated. But in double X production, whether you choose one scale or the other, you get, since the top virtual top effects, I mean, they are relevant. So, I mean, I don't know if in this case, if one can simply choose the renormalization scale of the top mass or the order of the top mass and forget it.
Mm-hmm. Okay, Marcel, I don't know if you have a further.
Yeah, I had an answer to the question about the asymmetries. It's a bit late, so we have to rewind a bit the discussion. I think the asymmetry is very interesting, observable. I've worked on this myself, but also Atlas has a program to measure the charge asymmetry at the LHC. And initially that was motivated by this possible discrepancy that CDF observed, and the enthusiasm decayed a bit when, of course, we didn't find much at the LHC. But I think it's still a very interesting observable to measure, because it's one of those observables that has a very specific BSM sensitivity. But if you want to talk EFT language, it is sensitive to the complementary combination of operators that the cross-section measures. So we need the charge asymmetry to do a global fit. And it's an observable that you can calculate very well. So we have very precise predictions. And it's one of those areas where the measurements are actually the dominant uncertainty and not the theory. So we definitely want to do it. Now, it's not an easy measurement at the LHC, right? We have 4 sigma evidence that there is a standard model effect. It's not something that pops out and you measure with good precision right away. But these measurements have an interesting BSN sensitivity, and we're keen to keep on doing those. Now, the question to theorists is maybe to which extent do we trust the uncertainty, right? Scale variations in ratios, it's all a bit delicate. One of the attractive features of this thing is that it has such a good theory uncertainty, but maybe more work could be needed to really make a solid estimate of the uncertainty that covers, again, everything that could possibly go wrong in the calculation.
Thanks, Marcel. What about the spin asymmetry? Do you have a substantial program for those as well? And by spin asymmetry, I mean, you know, triple product correlation between B jets and leptons, which in turn you can map into different helicity combination of the values of the TT bar quite easily.
So we've measured spin correlations, as you know, but
Yeah.
you're thinking of something more specific than that.
Yeah, there is a long list of observable that you call asymmetries that you can define, some of which can also capture parity violating effect, some can capture CP violating effect.
Yeah. Again, if we can show that these are sensitive to certain types of BSM, to certain EFT operators, and we have precise predictions for them, I think there is a good case to measure these. So if you want to point me to some literature with concrete proposals, that would be very interesting for us.
I'll do
And
that.
my understanding, if Massimiliano has the list of observables, all predictions can be pushed.
Yeah, in principle, everything is calculable, I guess.
Of course, it's not. I mean, at the moment we don't have the decay. So, but I mean, in the future, I think so. Theorists will be eager to compute. I mean, if there is interest, and we see that there is something which is also important, also in view of BSM studies, definitely would be interesting to take a look.
Yeah,
Sure, I can propagate the information I have. There's quite a lot in the public domain. Since we have opened the floodgates to BSM physics, wearing that hat, can I ask another question? I'm aware that we are running late. Is that correct?
It's fine. I don't know if our speakers and Gennaro is. Please, I think.
I think we can have a last question. Then
Okay.
We will have tomorrow a gathered town meeting at 11:30. So we can even discuss top physics if today's speakers are willing to connect as well.
I'm traveling.
But for sure, another question will be fine.
Okay.
All right, so this is actually a general question to everybody. One other thing which has been raised in the context of BSM physics is that measuring alpha S in TT bar samples is very interesting from the BSM perspective, because if you're looking at the effect of virtual object which couple strongly, say as quark or lately as of late vector light tops that you get in composite version of the standard model, they alter the QCD coupling constant evolution, especially if you pick up observable in the PV scale region where the masses of this potential new object would be living. There is a case for seeing effects from BSM in alpha S measured from TT bar, because clearly the standard model part evolves starting from 2MT. Whereas if you go and look at measuring effects of ESM, vector-like topless, quarks, whatever, in the alpha S evolution in other observables like jet, clearly the contribution from the standard model kicks in at very small q squares at some point, just obscure the contribution from whatever potential ESM physics is there. So the question is very general. What is the ultimate precision that you would expect in measuring alpha S from TT bar data? Because I'm keen to have that number so I could tell what are the theories with additional object to which that very simple measurement could be sensitive to. And there could be quite a lot of theories, because many of these new theories, right, they use the Higgs and the top, both or either of them as portal for themselves. So you also have funny effects where you can have interference between the top and the new top contribution and so on and so forth. Starting from
the point is clear. I don't know if from both the theory and the experimental perspective we can have an answer.
Remember correctly that I mean there are extractions, no, of alpha S from top data. I don't think they are competitive with precise measurements, but maybe I'm wrong. Maybe
well, there is the measurement from the cross section, and that this is limited
Yes.
the cross section by the knowledge of the luminosity. And however, there were ideas of extending that to differential cross sections in order to be potentially free from this limitation. And this depends on statistics. So there are ideas around. I think that it would be useful, well, it's been already done, I guess, but it's really useful if the theory community could indicate to the experiment which differential distribution are the one which are most sensitive to alpha S and less sensitive to other effects, in order to invest an effort given the large amount of luminosity we are getting in the next years. You know.
Yeah, the BSN community indicated the TT bar invariant mass, but that's the obvious one. I don't think they've done a thorough investigation of what other differential observables
Exactly.
up a large Q square, whether it's the PT or invariant mass, could be the most relevant one. But that could be an interesting activity that we could kind of prompt within this workshop, so within LFC working group. I agree. There is lots of interest, so I'm willing to compile some references in that respect, if that is of interest to this audience.
Yep, thanks, sure. Okay, now following the indication of our chair, I thank again Massimiliano for this very nice presentation.